Welcome everyone to this session. I'm going to talk about cracking the chaos ransomware. So to begin with, let's just define what that title means. So cracking a ransomware means that we can somehow subvert the ransomware, which is locking files, so the victim can't access them. But we can bypass that and get the files back without paying the threat actor. And a ransomware family is basically a number of different ransomwares which are all derived from the same original ransomware. So we're going to talk about cracking a family of ransomware. So this story begins on a dark place on the internet. It's a hacking forum called XSS, where a user wrote a post where they say something like, I don't really know Russian, but when I Google translated this, it said that I have developed this new ransomware. I'm going to distribute it for free. This is the builder. You can build your own ransomware. Go to this GitHub link. This link is now gone, but if you check on Web Archive or something like that, you're going to see that it was originally called Ryuk.net ransomware. It does not have any correlation with the actual Ryuk, which is a quite well-known big ransomware strain. This is something completely different. But it basically just hosted a zip file which contains the builder. So this happened back in June 2021. When we follow the poster of that original post, we see that there was a previous post by the same individual on another forum where this person claims to be the developer of something called the Backlight ransomware. And he's looking for, or she is looking for, a partner to do ransomware with. When we look at the code, we can actually, like just comparing Bagley and Chaos, we see that they are quite similar as well, so this seems quite probable. During the coming months, this ransomware keeps developing and new releases are published, one after other. I'm saying this is a ransomware because that's what it became after a while. In the beginning, this was actually wiperware, so it didn't actually encrypt anything. It just overwrote every single file on the system. It just destroys file. It says that contact this email, blah, 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 and pay, but it doesn't really matter if you pay or not because the files are overwritten. There's no decryption because they're not encrypted. But in version 3, they started implementing encryption, and the builder actually has a decrypter as well. So at that point, it's actually a proper ransomware, but with a small thing that it only encrypts files which are under 1 megabyte. All other files it destroys. So it doesn't really help, right? So, I mean, what I read in this is that it's more of a something trying to look like a ransomware, but it's a wiper. Just to give an idea what we're talking about, this is what it looks like. So this is the Chaos. It was called Ryuk.net from the beginning, right? But then they rebranded it to Chaos after someone pointed out that that name is taken. So it looks like this. You basically a GUI where you click and drag and drop, and you build a ransomware, and you configure the ransomware node, and blah, blah, blah. So what happens when someone distributes something like this? Well, something like this, you don't really have to read everything in here. It's just to show the graph of when we try to track down and see how big is this ransomware. So it's pretty much like all over the place. One notable case, though, happened here. This is the Azovstal steel mill in Ukraine. And you might have heard of this. It's a steel plant in Mariupol where there was a lot of reporting. They hid in the tunnels beneath and kept the city for quite a long time. One part of it that you might not have heard of is that Chaos ransomware was used against Azovstal during this time. And it was used pretending to be a ransomware. It also sent this link to some propaganda page, but it actually just wiped files and kept files under 2 megabytes. So this is the source code of the ransomware. And what you can see here in the first if, you see that, is this, nope. Come on. Never mind, I wanted a laser pointer. But you see in the first if here, if the file is below 2 megabytes, it actually encrypts the file. If it's under or over that size, it basically just overwrites the file with random bytes. So there is no way whatsoever to, at least you can't get it back by paying. Another interesting case, just to show the width of this. So we have everything from actually used as a cyber aspect in a kinetic war, all the way to decryptors are being sold on Roblox, which is a kids game. So it's like, this is what happens kind of when you distribute a builder for free for everyone to use, right? So this keeps going on, and we have, coming up to April, we have a lot of different rebrands, which are called different things, but they are just basically the same main branch. And one notable fork is Onyx, which later rebranded to VSOP. So what we're looking at now is a website operated by the threat actor. Most ransomware groups have a page like this. They're hosted in Tor, so they're hosted like an onion site, so it's extremely difficult to take it down. And what they do is basically, when they hack someone, they steal a lot of data, and they threaten to publish that data on their ransomware blog, as it's called. So this is notable in the sense that Chaos started becoming a ransomware group that is actually going after companies on a completely different scale, because it's a group of hackers that are actively working trying to encrypt companies. Another one is SolidBit, which is another ransomware group that uses Chaos. This one is a ransomware as a service, as it's called. That works, if you don't know, kind of like Uber. So they recruit freelance hackers. Anyone can join, and they give you a kind of a package with, like, here's the ransomware, here's the blah, blah, blah. Everything you need, you just need to hack companies, and then they share the profits. And that's basically how most ransomware groups operate these days. So when we're up to October, we have quite a big family. It's a lot of different, just rebranded, but there's also actual forks where they have changed stuff. So this is where we come into the picture. A company in Germany called us up, and they had been, fully compromised. So the CISO woke up early in the morning with a lot of missed calls. Everything is down. You hope like it's probably the DNS or something like that again, right? But this time it was something different. And pretty much because the way that ransomware attack works against organizations these days, it's not like, the ransomware used to work like a few years ago when it's a file that you like download, you double click it and your computer is encrypted. But instead they have an initial entry, maybe they phish someone or they send malware, they infect a client, then they escalate within the environment, and then they take over the systems that the IT staff is using to manage the environment. And then they use that system to disable antivirus everywhere, remove all the backups, and then finally push out the ransomware. So pretty much everything is destroyed and there's no backups to go back to. And that's what have happened to this company. So we started by doing the investigation, and we figure out after a while where this was sent from. It was sent from one of the domain controllers, pushed out as a GPO to everything in the environment. This is the old format when we look at an actual file encrypted by Chaos. What we saw, though, is that this file has a different format. So it's quite a significant change from Chaos. Everything else looked like Chaos, like all the functions was pretty much the same, but the encryption scheme had changed quite a lot. So both the mode had changed and like just the overall format, so like they save the key after instead of before and things like that. So before we go forward here, let's just get a look at what that would look like. So we are gonna try to encrypt ourselves here. And I guess it's a good time to say don't try this at home. So here we have a bunch of sample files. We also have the Onyx 2 ransomware. And just to show you what files these are. So they are, for example, my presentation that I'm doing here today. So we right-click, run as admin. Yes. And these prompts wouldn't normally show on the computers where this runs, but because I'm running it interactively, looks like that. But after a while, it has found the files. It says, you know, go to this Onion site, log in, and yeah, you can get your files back. And you can see that the files on my system are no longer a PDF file. It is called something .onyx. If I remove that extension, just to try, we're going to see that it's not a PDF file anymore. So that is what it looked like on that customer system, but not on just that isolated VM, but on every single system, all the servers, even the hypervisors, like everywhere. So we started looking into those encrypted files, and we saw that they are different. So we thought it might be worth looking into a bit more of this, and we saw another change. They actually changed the file size. So now it's almost 4 gigabytes. And you're going to lose a lot of data if you destroy everything larger than 1.4 gigs. But then again, you're also going to have a lot of PDFs, docx, Word, Office, whatever files that are, or config files and things like that are below that size. So in this case, they would actually mean quite a lot for the customer if we were able to save all those documents. So yeah, I started looking into what does this ransomware do. It creates a unique password for every single file. It generates basically a random. The parameter sent to this is 40. So this is going to give you a random string of 40 characters on that A, B, C, D, E, F, G set of characters. It takes that, it runs it in derived bytes. So it like derives a key and an IV, which is then used to run the actual encryption with AES. And the AES key is then stored in the end of the file, encrypted with a public RSA key. So these are not like something that someone made up. These are actual proper algorithms, right? We have AES, we have RSA. These are like, yeah, the stuff you're supposed to use. But if we look at that generate password again, we have something called random that is used to generate a random password. Sounds like something, it sounds random, right? But no, it's not really random. Not in a cryptographic sense, anyways. So if you go to the documentation, it says that to generate a cryptographically secure random number, such as one suitable for re-entering a random password, use something else, not this. And so I thought that this is probably one of these, like, you know, theoretical things, right? Like every other crypto vulnerability. So I have a colleague, he's called Carl. He's like he wrote some PhD in post-quantum crypto, which is like, what kind of cryptos do we need when we have quantum computers in 30 years? So he knows crypto way better than me. And so I asked him, and he answered that I already got a POC for that on my GitHub. So that was very helpful. So how is that going to work? Let's start by understanding how SystemRandom works in .NET. So we don't have to care really about the random function. We just have to care about the input value and the output value. So the input value is something called a seed. You give it, for example, 0, and it spits out something completely different. And it's just a sequence of random numbers. If you give it a 1, it's a completely different sequence. If you give it a 2, it's also a completely different sequence. And 3, the same thing. So far, so good, right? If you give it a 3, and then you instantiate a new random and give it a 3 one more time, you're going to get the exact same sequence of numbers. So that's the first thing. The second thing is if you give it -3, it's also going to give you. So it's the absolute value of the seed that it's going to use. So what is the seed? The seed is a 32-bit number, which means we have 4 bytes. 4 bytes can be used to represent 2 to the power of 31, well, 32, so you have negative and positive, but we only cared about the positives, right? Because it's the absolute value, which means that there's actually only around 2 billion possible passwords. And that's not that much, right? We can, with a decently powerful computer, brute force that. So that's the first part. Or actually, that's the key vulnerability, that the random is weak. But if we go to the next part, we see that they use CFB, which is quite an interesting mode of AES. It sort of works like this. So it gets the seed and the random that we talked about, and it generates that password. It puts it to the key derivation, and it takes out a key and an IV, and that's sent to this magic AES function. And what comes out from that is basically an encrypted IV. And yeah. So IV is a initiation value. Yeah, that's it. Initiation value. It's basically something that is not supposed to be secret, but it's supposed to be random and all sorts of things. But it's just something that is provided to the encryption function. Thanks for the question. And after that, the plaintext block is just XORed with this encrypted IV. So, and then you have the encrypted ciphertext. So what we know is that we actually have the plaintext of the files, right? We don't have the plaintext because then we don't have to decrypt anything. But we actually know the beginning of pretty much every single file, because you have something called magic bytes, right? So on a PDF file, for example, every PDF file in the world is going to start with %PDF uppercase. So we actually know if it was a PDF file, we know what the first 4 bytes were before. And it's the same for pretty much every single type of file. So we can take the first 4 bytes, we can XOR it again with the plaintext, and then we're back to the encrypted IV. So that's sort of the first step of taking this encryption back. And since we only have like 2 billion possible encrypted IVs, because there was only 2 possible billion seeds, we can generate a table of every possible IV for that, for everything. And that's just going to be 8 gigs. And that's going to be really, really quick to iterate. Especially like if we're smart and loading it up in memory and looking it up in a hash table kind of thing. So let's implement a decrypter. So we start with this first thing that we talked about. We have the first 4 bytes of, for example, PDF. So we map those bytes to the extension .pdf. We do that for every type of file that the ransomware actually supports, because it actually has a whitelist of what types of file to encrypt. They usually do that because if they encrypt everything, they're going to start with encrypting some, exe file, DLL file, something like that, and the system is just going to blue screen and nothing is going to get encrypted. So they need to actually explicitly say what files to encrypt. So we can find the magic bytes for pretty much every file that can be encrypted. And then we pretty much just iterate every file that the user has given us. We take the first 4 bytes. Then we get that encrypted IV by looking up what magic byte do we guess what known plaintext magic byte is going to be the beginning of this file. And then we XOR it from the ciphertext that we have just read, those first 4 bytes. And then we have a basically a table where we have every single IV for every file. And we just iterate that big database file and see, does it match? Or actually, we see if it matches, so we have a table, so we look up every file for every position. And if we have a match, then we know the seed, because we know the position in the file, and it's sorted by the position of the seed. So if we have the seed, we can do the entire thing from the beginning again, right? And then we can generate the password and the IV, and that's all we need to actually decrypt the file. So that's it. There we have decrypted Onyx and VSOP, as it's called right now. And the question is, can we then generalize this to the entire family? Because we have more than just Onyx that were looked at. And we looked into Chaos to begin with, which is the original. This one is still quite limited, right? Because it destroys everything over 2 megabytes. So it's not going to be that useful anyways, but it's, why not crack it? So we have some differences, which is that it uses 1,000 iterations in the key derivation, which means that it's going to be extremely slow to generate the key that is used for the encryption. It also uses CBC, which means that the mode works a bit different. It takes the plaintext and the IV and XORs them, and then it encrypts it with the key, which means that we can't use our clever plaintext trick here, right? So this one becomes a bit more tricky. But what we can do is that we still only have 2 billion possible passwords and IVs. And that's it. And that's 103 gigabytes, which, I mean, it's quite big, but it's not that big, right? I guess most of you have 103 gigabytes free on your disk, right? And if your entire company were wiped out, it would maybe be worth it to download a file that big. Problem is, on my computer, which is kind of powerful, it takes 203 days to generate this table because of that 1,000 iterations for every single key that you're going to generate. So this is actually super, super time-consuming to generate. But luckily, we got a supercomputer from Intel a while back, and I still have my colleague Carl, who knows Cuda. So he implemented like a Cuda script, which uses graphics card, which generated this database under a minute. And the bottleneck was really transferring it from the GPU and writing it down the disk. So, thanks, Carl. And Intel. So then we have cracked both Chaos. We have cracked Onyx, and actually Onyx 1.0, which is pretty much the same thing as Chaos 4.0. It was only until later where they changed the crypto, so it became something different. And then we have SolidBit, which is another ransomware here. Which is that one that was a ransomware as a service. That one is a bit different, not only because it's CBC just like Chaos, but it also uses, it's just like when they implement it, it's a bit, because they first generate 40 random bytes, then they clip, so they only have the first 16 bytes which are actually used to for the key. And then they do a completely different random, and then they get the IV that way. So we need to guess, we need to know both those values. And the problem when they do it completely separately is that we're going to need to test all the combinations of all the ones. So you're going to have, much more, right? You have 2 billion and then compare it to 2 billion. So it's going to be, yeah, way, way bigger. And keep in mind that the first table was 103 gigs where you didn't have that thing. So then you're going to run out of disk space pretty soon. So to crack that, I thought we were going to play a bit with SystemRandom, just to get a better understanding of how it works. So I guess first thing here is we have just some, yeah, by the way, I'm not a developer. I don't think this is the way you're supposed to compile C#, but stick with me. So you have a function, get random string, and it does exactly what that function in the ransomware did. So it generates a string which is the length, which is completely random. Then we have another one where you can explicitly set the seed. And then I have two functions which I want to show. One of them is print many, and the other one is print fixed seed. So let's start with just print fixed seed. So we have the length, which doesn't really matter, but let's say 40. And then let's set the seed 1. So every time you run this function, it's going to run with this seed 1. And it gives us this random thing. If we run it again, get the exact same thing. And we can run this over and over, and it's still going to give us the same thing. If we change the seed to, I don't know, 2, we see that we get something completely different. This is basically what I explained before, right? And the interesting thing here is, let's say that we print, we don't specify a seed, but we run the SystemRandom function just a lot of times. Every time we run it, we initiate a new random. And we just run it over and over and over and over. So let's run this function. We're not going to sleep in the beginning. And we're going to run it 100 times really, really fast. What do you think is going to happen? Like, we're going to run SystemRandom 100 times. We're going to get 100 different randoms, right? The seed is going to be different for everyone. Let's try it. Is that a bug in my code? Like, that can't be right. It gives the same random every single time. Let's try to add a sleep in between. So we just have like just 100, what is it, microseconds, something. Run it again. And now it's different. I just added a sleep. Okay. If we do, I don't know, let's say 10 or something. Seems like it's different, right? But there are some duplicates. So it seems like the seed is somehow based on time, right? So if we go back to this SolidBit ransomware, we see like just what I sort of said here is that the tick count is going to be 0. You're going to have duplicates. And what we realize if we read the documentation again is that the default seed is the environment variable tick count. And the tick count is the number of milliseconds since the system has last booted. Which means that when SolidBit generates both the key and both the IV in a very, very short time, it means that the key and the IV are going to be the same thing in 99.99999% of the time, if we're not super unlucky and it just flips. It also gives us another idea here. Maybe we can query the system boot time and then get the file last write time, and then we're going to know what the tick count was at the time of encryption. Then we don't have to actually iterate stuff. So we're going to be able to actually just get the seed, which means that this is extremely weak cryptographically speaking. Unfortunately, this doesn't really, we don't use this trick in the decrypter because it doesn't really support all the cases. Like, for example, the system might have rebooted after the encryption was run. Maybe the company that does the encryption wants to set up a new computer and run my sketchy TrueSec tool on and not run that all over the place. And then they just transfer files to that specific system. And then they're going to have different seeds. So I guess it makes sense, and it's still like quite fast to iterate the entire key space. So this means that the key is the IV, and we're back to having just 2 billion possible keys to iterate. And the other thing is that they don't even use key derivation in SolidBit, which means that we don't need a database because it's going to be fast enough to just iterate everything on the fly and just generate the database as we go. So there we have it. We have cracked SolidBit, we have cracked VSOP, we have cracked the main branch, and Astrolocker is another branch, but they shut down and released the encryption keys themselves. So we don't need to crack them. Then there's all these other ones which we haven't been able to obtain because they're so crazily spread out. But yeah, if you find something which uses something else, please send the sample to me. So before we move on, let's see if we can get our files back. So these are the files we just encrypted, right? Let's see, file item extensions. Because I renamed this before, right? And I'm going to break stuff if I rename it the wrong way. There we go. So let's copy these files to my underlying system. I'm going to remove the old ones. So there we have them. We can actually, now that I'm on the other system, actually look at the file just quickly. So you remember how a PDF file is supposed to look, right? It's %PDF in the beginning. This is just 1, 2, 3, 4, 5, 6, 7, 8 in the beginning. And that's actually the static salt that is used to derive the password. So that's going to be the same in every encrypted file, which is a possible way to identify the this specific strain. But yeah, as you see, it's just random characters, pretty much the entire file. This is encrypted. And then we see in the end here, it's something which does not look encrypted, because you see it's only printable characters, and this is a base 64 of the RSA encrypted AES key. So what actually happens, like if you pay the threat actor, then they're going to give you the private RSA key, which can be used to decrypt this blob here, because this actually contains the actual AES key that can then be used to decrypt the rest of the file. So yes, there we have a bunch of encrypted files. Then we go to, oops, I'm not going to be in my VM anymore. Let's see. We start our decryption utility. And it says to read the documentation before, and please do that. Both because a fun thing with this ransomware is that it, in some configurations, creates persistence. So persistence is that it will start itself up when the system starts up or some kind of event occurs. In this case, they use a link in the startup folder, and when someone logs in, that program will start. So the system will start encrypting again and again. The problem is that they write that before they run the encryption. So the persistence itself is encrypted, which means that it won't work. But if you run this decryption utility, then it will decrypt the persistence, and that might work again. So please, yeah, read the documentation for stuff like that. And as you see here, it's licensed under GPL free, which means that next Wednesday, actually, we will publish this on GitHub if you want to go in and read the source code and stuff like that. So what you do is that you specify the extension that you want to decrypt. You then select the decrypter. You can use this identify thing to see what ransomware, what specific strain it is you're affected by. Then you select the database file. In this case, it's the Onyx file, so it's an 8 GB database file. You can also download it if you don't already have it. Then we select the folder, which is, we store the files here, right? You can also run it for your entire system, of course. And then we do next, and it says waiting. And let's, yeah, it says decrypted. Thank you. And let's open the files, see if it actually worked. And it did. Yay. And I guess we can continue the presentation from this decrypted file instead. So what we're also going to do, aside from publishing this on GitHub, is that we are working with Europol. They run a project called No More Ransom, which is a well, the home of a lot of different encryptors. Some of them based on like actual keys, and some of them based on vulnerabilities, like this one. But if you, let's hope not, but if you someday find yourself a victim of ransomware, please check this site, nomoreransom.org, because they might actually have a decryptor for the ransomware you're affected by. So yeah, these are my backup slides, but the demo worked, I guess, so no need to go through these. Yeah, that's it. So we will release this as open source, as said. If you have any, if you need to use it or just find it interesting, please submit pull requests and all sorts of things like that. And yeah, thanks a lot for listening.